Welcome to the last installment on the nature of light. So we've discussed three phenomena that developed over about a 20-year period at the beginning of the 20th century. And we've seen in all three the only way to explain what's going on is to treat light as a particle, and a particle with momentum. And momentum is a particle property, even though light still has wavelength, it still has frequency, which are, and especially the wavelength, is a classic wave measurement. So we got to bring it all together. And it's going to be an answer that is still, if you will, some people aren't satisfied. Einstein was never satisfied with the answer. Others take a more philosophical approach and basically say, well, maybe our question is the problem, and the answer is basically telling us the question is a problem. I won't go down that road too much, but it's actually a very, very interesting and it's discussion, and it's been discussed for over a century now in many ways. So, in the three phenomena related in the previous pages, as I just said, we must treat light as a particle. Okay, we're going to choose. No. Okay, so photoelectric effect, Planck's explanation for black body spectrum, which was really started this whole thing off, and then really the final case to be made was the Compton effect. However, light still has to have a wave nature. That hasn't gone away to explain diffraction and interference and polarization, amongst other things. So that's very definitely a phenomenon that light exhibits, and the only way to explain that is Huygens principles and the physics that comes from that. So what is then the modern interpretation? Okay, well, the best we can say is, and it's kind of a compromise, but be careful of how you interpret it, because I've heard many people, and especially some who should know better, kind of state it incorrectly. So light has a dual nature. Sometimes it acts like a wave, i.e., or aka as you would say, diffraction, interference, polarization. Other times it acts like a particle. It can change its nature, but it never, and that's important, we have never observed it acting like both at the same time. Okay, so you can put it in a number of ways, but what is, in a sense, telling us light is whatever it is. We have developed in physics, for the overarching explanation of everything, that either you're a wave or a particle. Well, that dichotomy, okay, that maybe nowadays you say the binary way of looking at light fails. It just cannot fully describe it. It works really, really well with many phenomena, and in general you can get away with it, but if you really, really want to understand the nature of light, we don't have a word that really explains it. So we compromise and say it has a dual nature. Sometimes it's this, sometimes it's that. And how you determine what, and this also implies, and I think I might get to that later, is that the scientist's choice of experiment essentially determines its nature. And if you think about that, that's kind of odd. That kind of is counter to what science is supposed to be in terms of being objective versus what I just implied is subjective. Okay, now it gets even crazier. So around the time of Compton, a year later, a young physicist just finished his PhD. He's looking for something to study to, advance his career. A Frenchman named Charles DeBroglie. He asked a very simple question. All right, it's just a logical question to be asked based on what we just talked about before, and I'm paraphrasing and simplifying, obviously. If the classic example of a wave, okay, and remember, light was initially pretty much at the end of the 19th century, everyone was convinced it was an EM wave. If it can act like a particle, well, can the classic example of a particle, which at this point would be an electron, right, a little tiny piece of mass, one of the tiniest pieces of mass, can it act like a wave, right? So can a classic particle that has, like I said, mass, charge, volume, well, don't get into volume, but can it have wave-like properties, wavelength, frequency, can it diffract, blah, blah, blah. And I'm imagining DeBroglie said, why not? But that doesn't take you anywhere in science. You need experimental evidence for yes or no. And of course, the answer is yes. And this really starts turning our understanding of the nature of matter or waves on its head. But in hindsight, it kind of makes sense. Why should light be special? Why should it have this dual nature? Why can't particles have this dual nature? So he even went so far, and this is what's important, to make a prediction about such a wavelength of what we call an electron wave. So if an electron does indeed have wave nature, it makes sense to call it a matter wave is the more general term, or in this case, an electron wave. He basically said, all right, we know from previous that photons have momentum, and they also have wavelength, and they can be related. If you go back to the prior page, I'm just rearranging things, that the wavelength is simply h over p. Okay, and if the particle in question has mass, then we can take the classical definition of momentum, especially when it's at low momentum. At higher energies or momenta, the equation becomes a little bit more complicated, but we're going to stick with simple. You can just simply do the wavelength, if an electron has one, so I'm going to put an E just for here, but it could be any particle, is Planck's constant divided by the mass of the electron, divided by how fast it's moving. Okay. Now, if we go back, before I do an example of this, if we go back to the Compton scattering equation from prior, all right, let me scroll down here. Notice that this term in front is really h over mv. In other words, it has the same units, in other words, distance units, as the equation I just put for DeBroglie wavelength. This term right here is just a constant, right? A number between 0 and 1. So it makes sense that this whole quotient has to have units of wavelength or length. Anyway, so if indeed an electron can have wavelength, well, what value would it be, and then what experiment could we set up to verify this? So let's take an electron moving a tenth the speed of light, which is very easy to do. We could just as well do this equation for near the speed of light, but it's really not going to change things dramatically, just an order of magnitude. So if we apply, all right, we can say the wavelength is equal to 6.63. Again, I'm just going to go with the classic SI units. I'm not going to put in units here. M of electron, it's in the front of your reference tables. That becomes a very important number right now. I might be 9.11, but it doesn't really matter. Negative 30th. And then the velocity we said is 10 to the 7th. Okay, plug in the numbers, and as you might expect, you're going to get a pretty small number because Planck's constant there. But because of the tiny mass of the electron, it's not as small as one might expect, and we get around 7 times 10 to the negative 11th meters. Okay, so look at that number for a second, the negative 11th part. You have seen over the course of a few weeks the wavelengths of light, typical wavelengths of light, are on the order of hundreds of nanometers, essentially 10 to the negative 7th. So this is about 4 orders of magnitude shorter, and so you should be able to understand where exactly in the electromagnetic part of the spectrum would this be comparable to. Okay, so visible light's negative 7, it would make sense ultraviolet would be negative 8th, maybe negative 9th, and you keep going, you see we're now into the X-ray gamma part of the spectrum. Okay, so if you are a physicist and you want to verify de Broglie's prediction, you want to show that this wavelength, or the electron is acting as a wave, it has wavelength, so what experiment would you do to test if something has wavelength? So think to yourself, pause right now and think to yourself, what kind of experiment would show the wave nature of something? And hopefully something becomes immediately obvious. You can go back to our initial discussion of how we showed that light was a wave. Okay, we're going to look for diffraction and interference. So how do we do it? We have a beam of electrons that supposedly have a wavelength, and we look to see if they will diffract. And I should add interfere, but I'll just leave it through tiny openings, right? Tiny slits. Well, if you think about diffraction, what we learned, in order for you to really see diffraction, right? If we have a diffraction angle, it's basically equal to or proportional to lambda over d. So we have a tiny wavelength. Well, d has to be comparable to that wavelength to really notice a significant angle. Well, the diffraction gratings we've used in class for visible lights just don't cut it, because if visible light's 10 to the negative 7th, our diffraction gratings had spaces around 10 to the negative 6. So we can't manufacture these. So how on earth are we going to get openings that are roughly 10 to the negative 11th? Well, nature provides us something, and that's crystals. In other words, certain minerals, salt is maybe a classic example, where if you have a regular array of atoms, between each atom is essentially empty space. Okay, certainly there is force fields between them that are, observed as bonds, but it's literally empty space. So one of the more important experiments that you need to be aware of, and this especially for the IB, is the Davis and Germer experiment and Thomson. This is actually J.J. Thomson's son, working about 30 years later after his father had discovered the electron. Anyway, this has been verified. So when Davis and Germer did their experiment, they shone electrons at crystals. They indeed saw interference and, diffraction and interference. And I'm going to talk a little bit about some of the detail here, looking at this diagram, just to help you make a little bit more sense of it. Okay, but I'll tell you right now, this experiment has been repeated for bigger particles, protons, where the wavelength is going to be even smaller because the mass part right there is going to be bigger. Neutrons, atoms, even large molecules. Okay, in class, since I don't want to take up too much time on here, we can even look at what would be, and maybe this is something you can do, what would be the DeBroglie wavelength of a baseball thrown by, let's say, a major league pitcher where the speed is around somewhere, let's just round up 10 to the 2 meters per second. I know that's really high, but we're just ballparking. Okay, but anyway, here is the essence of Davis and Germer experiment. They have a nickel crystal where the spacing of the crystal is well known. Okay, well, I take that back. Yeah, it was well known. Okay, they shine in electrons, and what's important here is the voltage that they accelerate the electrons gun. So you have an electron gun, much like we showed with the E&M apparatus way back in the fall. You put, in this case, 54 volts across it, so don't give it a ton of energy. And you shine it at the crystals. And what's going to happen if I look at this picture here, here are the individual crystals with the spacing, is they will interact and the electrons will scatter. Okay, and when they scatter, okay, they will eventually, these will interfere with each other, and you look for an interference pattern. Well, if you apply the theory right here, what would be the wavelength of the electrons based on this energy? You get about 1.67 angstroms. I think angstrom is 10 to the negative 8th. Okay, so based on this equation that d sine theta equals your wavelength, right? That's our classic diffraction equation. When they looked at this, here is a graph, and they saw a peak in the graph at around 50 degrees. So that tells us, oh, there's constructive interference going on here between these two or more scattered photons. And if you apply that, you see you get 1.65 angstroms for a supposed wavelength of 1.67. So it matched very, very nicely. Okay, and so 1924, DeBroglie proposed this. 3 years later, Davis and Germer do the experiment, and in 1929, DeBroglie wins the Nobel Prize, which is unheard of. That's a quick turnaround, but good for him. So this idea that everything in nature at its most basic level is not either a particle or wave, but is one or the other depending on what you do. It changes its nature, or we just don't have a word to describe its actual nature. I'm not going to go into the semantics of that. Okay, but what we want you to understand is that all entities in nature are just as much a particle as they are a wave. So it's not like light is 99% of the time a wave, and for these really weird things it's a particle. No, it's just as much a particle as a wave. And the same for an electron. That's even harder for, I think, people to swallow. An electron, which is always taught classically as a tiny piece of matter, it is, but it's just as much a wave. This has really, really weird implications that's going to be exploited by a guy named Heisenberg. And that's where we're going to start going next. And this is now, he, along with a guy named Paul Dirac and Wolfgang Pauli in the 1930s, start developing the basis for what is modern quantum mechanics, which we're just going to touch upon a little. Let's call it quantum, because the math involved with it is extremely complicated. Implications are even weirder, but nothing we have ever done in the past 100 years has done anything to contradict any of this.